Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am super happy to have Stephanie Douglas with us today. Hello, Stephanie.
Hi, Frank. How are you?
I'm doing awesome on this March 8th of 2024 as we record this. And it is spring in Phoenix, and we're getting a little rain today. So we're going to get some April flowers. And Stephanie, where are you located at?
So I'm at Lafayette College in Easton, Pennsylvania. So we're right on the eastern border of Pennsylvania with New Jersey.
Mhm.
We've been getting some rain here too. I think a little bit colder probably than Arizona is getting right now.
Probably right now. Is there still any snow on the ground?
No, not really.
No, all in one.
We've had some plenty of above freezing temperatures recently, so it's
Hmm.
pretty much all gone.
Very cool. That's an awesome bookshelf behind you.
Thank you.
You got a lot of toys. Little
Yes, I
Stephanie.
like to decorate my office.
Very nice. Very cool. And Stephanie, what do you like to do for research?
So my research focuses on the rotation of sun-like stars and lower mass stars, in particular calibrating the evolution of rotation with open clusters.
Nice. Very cool. And that is going to bring us to this very awesome. As soon as I get my sharing button up, it's very awesome. APJ article. It is open access. It's the open access era, people. Go grab a copy for free. Get one. Constraining stellar rotation at the zero age main sequence with TESS and Stephanie. Take us away.
Thank you. So before we get going, I would like to thank my co-authors on this, Phil Cargile at the CFA, Sean Matt and Angie Bryman at University of Oklahoma and formerly University of Exeter. Jose Perez Chavez is currently at Howard University.
Mm-hmm.
Chelsea Huang and George Ju are at University of Southern Queensland, and Nick Wright is at Kiel in
Very
the UK.
good shout out.
And so our focus in this work was to calibrate the evolution of rotation at about 40 million years.
Okay.
So I'll get into why the ages are a little bit complicated later. But we picked 5 open clusters in the TESS southern field of view.
Okay.
And looked at close to 1,500 stars and got rotation periods for a little over half of them.
Okay.
And part of the reason we did that is that this is an age that wasn't well constrained empirically, but it's a very important age for the theoretical rotation of these stars.
Yes.
So we go into testing one example of a model with these and using a new method called tau squared. It's kind of like chi-squared in 2D.
Okay.
So broadly, for those who aren't familiar with rotation, when stars are young, we talk about them spinning fast, and when they're old, they spin slow. But that is starting on the main sequence. So when stars are on the pre-main sequence, remember, they contract. And so to contract, they have to spin more rapidly to conserve angular momentum.
Okay.
And so while they're on the pre-main sequence, they're contracting and spinning up, and then they reach the main sequence, they stop changing their radius, and so they can start to lose angular momentum via their stellar wind.
Okay.
So we have this transition point but from spin up on the pre-main sequence to spin down on the main sequence. And so that's the zero age main sequence. And it's this spot that we thought at least we didn't have good calibrators for the angular momentum.
Okay.
And so this was a challenge for people trying to work on the theory of angular momentum evolution. So before TESS, one of the challenges with this age is that most of the clusters are in the south, and they're basically all pretty sparse on the sky.
Okay.
So, less access to observatories where you can do these long time domain surveys. And even if you're able to do that, you're not able to target many stars in a cluster at a time.
Yeah.
This turned out to be kind of funny. I was inspired to do this by Sean Matt telling me, oh, we don't have any constraints at this age. And it turns out there were some in the literature for sun-like stars. Everyone had just kind of forgotten about them or missed them when they were published. Only 11 of them are actually for solar mass stars,
Okay.
roughly. There were plenty for K and M dwarfs from Jonathan Irwin's work, and then a smattering of the higher mass stars from a handful of other papers, mostly from the 90s and then a little bit in 2011.
Okay, cool.
So what the goal was here was TESS has this huge field of view. It can capture lots of stars at once. And because these clusters are relatively nearby, they would be bright enough that at least the sun-like stars we hoped we could get without too much blending and contamination from other nearby stars.
Yeah, okay, cool.
So if we scroll down, let's see. Actually, I said I wasn't going to go out of order, and now I am. So let's jump to figure 3 actually first.
Figure 3, let's take a look and get a goal. Figure 3 with this big one. Okay.
Yes.
There we go.
So this was the state of stellar rotation before TESS. So this is rotation period versus Gaia BP minus RP color. The different symbols are just 3 different clusters in the sample that all have similar ages. And those the blue triangles are mostly NGC 2547 from Jonathan Irwin. And that's mostly the lower mass stars. The higher masses are IC 2391, IC 2602 from Patton et al., Barnes et al., and Messina et al.
Okay, cool.
And so, I'm gesturing with my mouse like I can show you things. So you can see there's kind of a
point me to I'll go.
A slow rotator sequence at the upper level of this sort of cluster of points, and then a smattering of faster rotators below that. And then the lower mass stars make this kind of slanted distribution over on the right.
Yeah.
So,
okay.
And so these are some of the features we're trying to figure out, replicate with the models. And so if you look about at a G2 around, or G2 to K0 around a BP minus RP of 1, there's enough stars that we can kind of see where the slow rotator sequence is, but we would like to get a much better sense of where that is. So around a period of maybe like 4 or 5 days up there is where the slow rotator sequence is.
Okay.
So we started out assembling a bunch of membership catalogs. We used Gaia and our own analysis of Gaia and a couple of catalogs from the literature. And one of the challenges actually turned out to be figuring out how old these clusters are. So if you scroll up to figure 2.
Okay, figure 2 and cluster ages, there we go.
Yeah. So if you look through the literature, so this is any paper I could find since 2010 with at least one of these, or with at least 2 of these clusters in it. I didn't worry about single cluster papers that tries to derive ages for these. Mostly through isochronal ages. There's a handful of like lithium depletion boundary stuff. And nobody agrees on how old a particular cluster is, or even the ordering that they tend to be in. IC 2391 is often on the older end, but not always. And so what we decided was that most of these measurements fell between 25 and 55 million years, which is those vertical dashed lines. And so we just decided to say, all of our clusters are one age population. We're going to keep, and we're just going to combine them all together and say it's 25 to 55 million years old.
Fair enough.
That turns out to be enough for the point that we are with the models as well.
Okay, fair enough.
So
good.
So if we scroll up now to figure 1.
Sure, figure 1, and we got color magnitude.
Yes, so this is now showing the membership of the clusters. So there's one panel for each individual cluster and then a combined one at the end. So in the individual panels, any point there was a member in at least one of our input clusters. To be considered for analysis further in the paper, it needed to be in at least 2 of the catalogs.
Okay.
So that's the colored points are things that we actually kept and are plotting in later papers, but even the gray points are included in the final catalog. So if you want to go get the periods for those, we do have them.
Okay, and remind me of the difference of the gray points in here.
Oh, sorry. Gray points are a member in any of our input catalogs,
Got it. Okay.
colored points had to be in at least 2.
I'm with you. Thank you.
And then what's shown in the bottom right panel is all of the members that we kept that were in at least 2 catalogs overlaid on each other, just
Yes.
so you can see what main sequence turnoff there is at this age. They all basically overlap with each other. And so this is just another piece of evidence that
Yeah.
lumping them all together in a roughly single age population works pretty well.
Yes. Yes. Okay, I'm with you.
So that's our initial sample. And then we went on to measuring rotation periods. So if we can scroll down now to figure 4.
There's something. Ooh. Okay.
Yes, so this is showing our 5 clusters in the TESS field of view, just for cycle 1. So sectors 1 through 13, although obviously we don't use all of those. So you can see that each cluster that we have, almost every star in these clusters is included in at least one TESS sector, and many of them are included in multiple TESS sectors.
Okay.
So I analyzed light curves from Luke Boma's CDIPS analysis, which is the cluster difference imaging photometry.
Okay.
Something about that. And then from Chelsea Huang's QLP light curves that were produced by the TESS team themselves. So I searched for any match between our cluster members and those 2 catalogs, and I looked at each sector individually and picked the best one.
Yeah.
Because these are relatively young stars, we knew that their rotation periods should be less than 10 to 12 days at this age. And so doing one sector at a time was generally fine.
Yeah.
If anything looked a little bit longer, I may have done some like boutique analysis on that one. But in general, we expected them to be rapidly rotating enough to not worry about that split off in the middle of a TESS sector.
Yeah. Okay. Very nice.
So if we scroll down then to figure 5.
Okay. Ooh, here we go.
So this is some examples of common things that we flagged in the period table.
Okay.
So the black light curve in each panel is showing just the full light curve for that sector. And then the green and purple are phase folded at the 2 predominant peaks in the periodogram. So I forgot to say we used Lomscargel periodograms to measure the rotation periods. So, and then on the black full light curve, there are vertical lines, and those are just saying they're spaced out by the measured period. So in the top left, the dominant period is 5 days. So the green dashed lines are spaced every 5 days, and the purple ones are every 2.7 days. And so it's just to see another way to look at the periodicity of the light curve.
Yeah, nice.
So if I saw that, or if the light curve looked periodic, then we would flag it as good. This is one where when I look at the full light curve and the phase folded light curve, it doesn't look terribly nice. So I would flag that as like a bad detection. In the upper right, this is a double dip light curve. So we think this happens when you've got spot distributions on both sides of the star. And they're evolving at different rates. So you go from maybe seeing half the period to then if one spot group gets bigger than the other, you'll get this double dip pattern. So the periodogram detected the green period, which we think is actually half of the real period, where the purple phase folded light curve shows what's the more likely period.
Okay, I'm with you. Yes, yes.
In the lower left, this is just an example of a really common systematic in TESS that didn't get removed by any of the trending algorithms.
Right.
And then in the lower right is an example of a star where we actually detect 2 periods. So there's a 0.38 day period, and which is that shorter period, and then a 3.5 day period that's overlaid on. And so we flag these stars where we find multiple periods, and there's a strong likelihood, especially when the periods are so different like this, that this is actually a binary star.
Yes, yes, yes.
Um, so we do flag them as candidate binaries as well.
Okay, cool, cool. Come
So
back.
I went
Yeah.
so I went through every light curve twice, at least, to flag these and do quality control on the periods.
Yes.
Because TESS is noisier and a shorter baseline than the work I'd done with K2 before,
Okay.
I was a lot more strict about what I considered a good period. So with K2, I had a tendency to err on the side of letting things in. I did the opposite with TESS.
Okay.
So the yields are, for me at least, are lower than what I got with K2. But we still got, in the end, over 800
Nice.
period, most of which are new for these stars.
Very cool. Okay.
So we can go down to the next figure.
Okay. Five. Period validations. Oh, I do want to just mention,
Oh,
we should say something about this big table 4.
yeah, I couldn't remember what order everything was in. Yeah,
Yeah.
so we have a catalog with all of our cluster members, or all of our potential cluster members. So there's the Gaia DR3 information,
Mhm.
information from the TIC. HDB scan is the membership analysis we did ourselves. Then there's also info to cross-match with the Gaia ESO survey and Kentakaran, which were the other 2 catalogs we used.
Yes.
And then we also got stellar parameters from an analysis of a code called Minesweeper.
Yes.
And so that information is included as well. That's where we got stellar masses. And then starting with row or column 41, P wrote, then we're getting into the actual TESS analysis. So rotation periods with what was the power on the periodogram peak, quality flag,
Mhm.
the significance thresholds. We did a bootstrapping test to make sure we're getting a real signal and not something from the windowing function.
Good.
Flags for multiple periods, spot evolution, which is that double dip period,
Yeah.
or potential blends. So I'll come back to the blends bit in a minute. And then we also include any literature periods
Nice.
available. And if we actually use the star in our analysis in the paper, then that last column has a flag of 1. If not, those are still in there. So if people want to look up the star, they can.
Nice. Very good. You didn't throw it away. Very nice.
Yeah.
Very good. Cool.
And
Okay.
then let me talk about the blends for a second, actually,
Okay.
that are
Sure.
these columns 50 through 54.
Yep.
So because of the size of the test pixels, I did not do any sort of visual checks for blending, but instead went through the Gaia catalog, looked for nearby stars that were
Um,
at least from 3 magnitudes fainter than the target on brighter.
okay.
So anything that's fainter than 3 magnitudes of the target, injection tests determined there's not a high chance of that contaminating the light curve, so we ignored those.
Okay.
Within 3 magnitudes, you have a stronger chance of contaminating the target. So what we flagged for, the exact details are in the paper, but we checked for nearby stars, down to fainter, 3 times fainter, or 3 mags fainter than the target, and also stars that might be a little bit further away, but that were brighter, and so can contaminate a larger number of pixels.
Yeah. Okay.
And so then in the catalog, I also included what's the nearest neighbor in Gaia and what's the magnitude difference of that neighbor, and what's the brightest star within an arc second, and what's that magnitude difference.
Good.
And we include the contamination info from the TIC as well. That was up earlier,
Yes.
but that was based on an earlier Gaia data release, and there aren't values for all of our stars. So you've got both those pieces of information if you wanted to do a more strict blending cut than we ended up doing.
Okay. Nice. Very cool.
And yes, this is available in full from the journal.
Very cool. Go get it. Okay. And then we were on our way to figure 5.
Yes. So this is our results.
Okay.
It's like the CMDs. We've got a panel for each cluster individually, and then a combined panel in the lower right. So within each panel for the individual clusters, the solid points are a high quality test detection.
Yeah.
Open points are a lower quality test detection. And then the gray points that are open are literature detections for that same cluster. So
Gotcha.
you can see how things have changed. Yeah, for NGC 2547,
As
there's a
well.
lot of those low mass stars already. And then for IC 2602 and 2391, in the lower left and middle right, there was sort of a much more scattered distribution of points, and you can see that we filled in a lot of that space now.
Very nice. Very nice.
And then in the lower right, we've combined all of the points. So anything with a test period is shown in gray as a circle, or with a high quality test period. And then the black solid dots are things that are definitely not blended according to our Gaia analysis. And the open black circles are maybe blended. And then unfortunately, anything that's left as gray has a probable star that could be contaminating its light curve. So what we did for the analysis when we actually compared to models was to stick with a smaller sample, which is these black points that are not blended, plus the blue stars, which are anything with a literature period where we had concerns about the test period.
Okay.
And I did actually test the analysis later in the paper on the full test sample, including blends.
Good.
And you get a similar result to what we get with this more high quality sample. But just for the sake of trying to get the best result we can, we did stick with this smaller high quality sample for the next analysis.
That makes sense. Very cool.
So
Okay.
now, so that's the data. And
Yes.
now we can go on to talking about the, oh, no, sorry. There was a couple other data things.
Okay.
So no, there's two more data plots. I just forgot about them.
Okay. Before we go down, oh, the literature ones.
Yeah, so figure 7. So this is a comparison to literature data for these 3 clusters. And so IC 2391, we have data from Patton and Simon 96 and Messina 2011. So there's a 1-to-1 line that most things fall on. The dashed lines on either side are either twice the period or half the period. So these are really common harmonics to find if you're measuring rotation periods at different times, or even just with different detrending algorithms.
Yeah.
So we don't worry about those.
Okay.
There's one interesting one down here in IC 2391, the 2 dots connected by a line.
Yes.
That seems to be, that's where we have 2 periods from Patton and Simon, but the 2 stars of this binary are blended in TESS. And so we only measured one, a shorter period in TESS, but in reality, it's actually 2 stars, and we only caught one of them.
Right.
And then in IC 2602, we actually did very well. In that case, the vertical line that connects the 2 points is a multi-periodic star in TESS.
Okay.
But we found 2 periods in the TESS light curve. One matches the literature period, and the other is probably a binary companion.
Correct.
And then finally, over on the right is NGC 2547. So this is where we have the most data from the literature, but it's the low mass stars, and those are the ones more likely to be blended. So we get some things that are aliases, which are these light gray lines that are sort of fanning out.
Yes.
That's where there might be an alias in the ground-based data. So they're all 1-day aliases, where you have issues with windowing when you can only observe every night, say a half-day period, you're not going to detect correctly.
Yeah.
And then vertical lines again are between multi-periodic stars. And then this again is because it's our most compact cluster, and at the faint end, we had the most issues with blending. So there probably are some issues with assigning the correct period to the correct star in TESS with this cluster, which again is why, to be sure, when we did our model analysis, we stuck with the literature periods, which have a higher angular resolution.
Gotcha. Okay. That's important. Okay.
And then if we go down to the next figure.
Okay, I'm with you. Just gathering. Okay.
Oh, yeah.
I'm with you. Okay.
So then this is comparisons with two larger studies of rotation in TESS from Kunkel and Featheroff that were done pretty close to the completion of this paper. And this is again a comparison of the, we've got a 1-to-1 line, and then I've also indicated blending because one or both of us would have had problems if there was a blend. And overall, our periods end up being very consistent with the periods from these other literature studies. Kunkel et al. Listed a period for every sector for a given star. So that's those horizontal lines.
Okay.
So that's why sometimes we agree with their results and sometimes not. And a lot of the ones where we don't agree are blended. So, which are the gray symbols.
Good to raise
So,
that. Yeah.
yeah, so overall, between this and our comparison to the ground-based data, we think we have pretty solid periods.
Yes.
May have been overly zealous in rejecting some things, but that's why we included everything. People can make their own cuts if they want to use this data later.
Right. So we stuck with the gold sample.
Yes. So then if we go down to the next figure, I think then
We go through upper scope, model data comparisons, and
yeah, and I'll talk through that. It's just easier. I like to do it just with the figure. So next we get to looking at models of stellar rotation. And so the thing that I always say and that we say in the paper is we did pick these models that Sean Matt and Angie Bryman have worked on. And that was because we had access to them, obviously, since they're collaborators on the paper. These are not necessarily the best models out there. We're using them as an example to test this method of fitting on this particular data. And as I'll hopefully mention later, there is a goal in the future to go back and do this comparison with other models as well. So, so for more information on the models themselves, you can look at Sean Matt's 2015 paper and Angie Bryman's 2021 paper. And the models that we use are basically from those. So in each case, we initialize our model using the distribution or an approximation to the distribution of periods in upper SCO. So that's what's shown here. So we have period versus mass, where the points are observed data from Louisa Rebel's paper on upper SCO, showing a period as a function of mass. And then the green histogram in the background is the number density of points smoothed by a kernel density estimator in each mass bin.
Okay.
So the goal was to capture the broad shape of the upper SCO distribution, but then to not get caught up by having these periodic outliers having a strong impact on the rotation distribution that we're predicting at later ages. And we actually only go up to 20 days, which does leave out a couple of the slowest rotators in upper SCO, but we don't think that affects our results very much. And so you can see that the darkest regions of the model are that dark green, and that's underneath where we have most of the points.
Yes.
So for everything future, when we show the model, we're just going to show the that background 2D histogram where the darker green indicates that the model is there.
Cool. I'm with you.
So, and then I don't think I have a good illustration of this. So we created 3 models. So all of them have the same initial condition. And we're starting at, we put the cluster, or we put upper SCO at 8 million years.
Okay.
So this should be after disks are mostly gone. And so that's our starting point. And then we modeled what we call the classical model. And Angie coined these terms in her 2021 paper. So the classical model is the model from Matt et al. 2015. So this is an older model for the magnetic wind work. The standard model does a better job of replicating low mass and rapidly rotating stars. at least based on comparisons to the Pleiades and Persepi in Angie's paper. And then we have the zero torque model. So this includes the
Okay.
contraction that you get from spin up, or the spin up you get from contraction on the pre-main sequence, but then there's no magnetic wind breaking at all. So this was kind of our baseline control model to see where the magnetic wind starts to have an effect
Okay.
on distribution of periods.
Okay.
So if we scroll down to figure 10.
Yeah. Okay, figure 10. Tau squared, period versus mass. Here we go.
Oh, there's like a weird missing gap in the
Oh,
model.
right here.
Yeah.
That's probably just a rendering issue.
Okay. So yeah, for viewers, it shouldn't look like that.
Shouldn't look like that. This is filled in. This is probably a rendering, and we'll check on another PDF.
Yeah, I know in my copy it doesn't show that. So yeah, I think it's just anyway, it'll be okay.
Yeah.
So now the black points here are the data from our 25 to 55 million year test sample at the ZAM. So it's the same data in every plot. The top row is a linear period distribution. The bottom row is a log period distribution. And so we've binned the models differently for each of these fits. And this is where you can see the effect of this tau squared fitting method that we're using. So tau squared is analogous to chi squared, but it works in 2 dimensions. So you're comparing the density of a model to the points within a given bin that you actually observe. So you're going to get points for, or effectively get points for having observed stars where the model has a high density, and you're going to lose points when there's observed points that are not within the model, or they're in regions of lower density.
Yes. Okay.
And this panel is trying to illustrate that visually. So we've got in the middle is the best fit. This is the standard model from Bryman 2021. So the best fit model from a linear or a log fit is in the middle column. And then we went lower or higher according to the probabilities. So we've got on the left 20 million years for both, and then on the right 130 or 150 million years.
Okay.
So what you can see is that on the left at the younger age, the color of the models is more uniform. So the number density in each bin is more similar. So we still have a wider range of rotation periods at a given mass.
Yes.
And then when we get to the middle plot, you can see there starts to be an overdensity in a similar region to the upper envelope, the slow rotator sequence of the data.
Okay.
And so this is good because we want to develop a concentrated slow rotator sequence in the model to match the data. And then all the way on the right, when you get to older models, you can see that slow rotator sequence is actually even more pronounced, but it started to move slower than the data itself. And if you look at the tau squared values themselves that are written on each panel, so like in the linear fit, we go 1301, 1258, 1323. So the lowest tau squared value corresponds to what by eye looks like the best fit to the data itself.
That's a good thing. Okay.
So we did this for each of the 3 models. So we have the classical, the standard, and the zero torque in both a linear and a logarithmic period binning, because those capture different features of the period distribution. So we've got, so we've got 6 total fits. We also did uncertainty analysis, basically taking the best fit model, redrawing a synthetic data set from that, and then refitting the models to that synthetic data set 100 times each. And also resampling the data within the mass errors and refitting there. So we got uncertainties both on the model and on and from the stellar parameters themselves.
Okay.
So if we scroll down to figure 11 or table 5, whichever one comes first. I think it's
do both. We'll do both.
Yeah, we'll get to both eventually.
Figure 11. Let's.
Yes, here we go. So what this is showing now is tau squared versus model age for the linear fits and the log fits.
Yeah.
And they're very similar. There's some slight differences in the numbers, but they're effectively the same. So what we can see, um, the lines correspond to the different models. So the dotted line is the zero torque, the solid line is that standard model, and the dot dash line is the classical model.
Okay.
The triangle points with numbers next to them indicate the best fit age for that model.
Okay.
And then the solid bars at the bottom of each panel are the uncertainties on that best fit age.
Got it. Perfect.
So if we look all the way on the left, and we can just focus, let's just focus on the log fit.
Okay.
As I said, the linear fit is gives basically the same result.
Okay.
So on all the way on the left at the youngest ages, the tau squared fit is improving for all of the models together until we get to 19 million years.
Right.
And so that suggests that up till 19 or 20 million years, the only thing that's, or the most dominant thing affecting rotation evolution is just that contraction dominated spin up.
Correct.
Then after that, even though we haven't technically reached the zero age main sequence yet, the zero torque model diverges from the other two models that include a wind torque, which suggests that the wind is starting to have an effect
Cool.
on the rotation distribution even before we get to the zero age main sequence.
Yes. Very
So
nice.
the zero torque model reverses, it starts going to worse tau squared, and it just stays there. So yeah, so we aren't worrying about that now after the 19 million years.
Right.
Then we have, so now we have that dot dashed line for the standard model, which is the older wind torque. And the solid line is what we call standard torque, which is that update to do a better job with lower mass and faster rotators.
Perfect.
And so both of them, you have sort of maybe a local minimum around like 20 to 25 million years. It's not super pronounced in this particular plot, which is when that wide distribution is passing the data as it's still contracting.
Yeah.
And then we get a global minimum in each line that's actually where the models best match the data.
Got it. Yep.
So one thing to note is, right, primarily isochronal ages say that these clusters are 25 to 55 million years. Neither of these best fit ages obviously are matching that. But the standard model, this new model, is getting closer to the age we actually expect these stars to be compared to the older model. So our models for angular momentum evolution and magnetic wind torques are improving. Not there yet, but we're heading in the right direction.
Right.
And if you look at those bars across the bottom that represent the uncertainties on these fits, they don't overlap. And so this data set and this method are able to distinguish between models with different prescriptions for the stellar wind torque. And so that's going to be very important for applying this to a larger suite of models, hopefully at many other cluster ages.
Yes, very nice.
So we can, if we go look at table 5, that's basically giving these results just in tabulated form. Again, we have the linear and the log fits with a best fit age for each model. And then the confidence intervals that we derived from both. So the model is where we made a synthetic data set out of the model itself and refit it to itself.
Yes.
And the mass confidence interval comes from resampling the data distribution within the mass errors.
Okay.
And so generally the thing that dominates is the model uncertainty, but we do get a little bit of a range from the stellar parameters themselves.
Yes. Very cool. All right.
And so that's pretty much where we are. We've got this great new data set that we hope other theorists will use to calibrate their models at this young age. And we've shown that this tau squared method can be used to distinguish between different stellar wind torques, prescriptions for that,
Nice.
and that our models are improving, even if we aren't quite
Not quite there. That's right. Getting progress. Progress. Very cool. Very, very nice. Stephanie, I want to thank you so much for walking us through your very lovely article. Very cool.
Thank you for having me.
Sure. And you kind of touched on it a little bit as we were going through. And so let me push on it a little bit. Where do you think we go from here, given the published article? Or are there additional data sets and tests that are just sitting there waiting to be done? Are there additional clusters that could be used? Is there you mentioned some of the stuff on the improvement of the models, and just sort of next steps? Where do we go from here?
Yeah, so I think, yeah, there's going to be a wealth of periods coming out of TESS, especially for these nearby clusters and moving groups. One thing I think is an important next step is to get a uniform sample of clusters, probably from data sets that are already in the literature. K2 and TESS and Kepler have given us this great distribution of open cluster periods. So taking those, getting, uniform ages, uniform stellar parameters, and then doing tau squared fits to all of them, I think is going to be very important. And not just with this one example model, but using other prescriptions for the stellar wind torques, other models that are out there,
Sure.
And comparing those at different ages as well, starting to see, what's working, what's not across all the models we have access to at this point. So that, I think, is a big next step. Personally, I'm very interested in how this stuff changes when you've got another star in the system, so the binary stars.
Yes.
So we do have a little bit of speckle imaging data for these clusters. I'm hoping to get more. And I'm working on rotation and multiplicity in some other open clusters as well, to see how that changes the evolution. Because right now our models assume every star is single, and we know that that's not the case.
Cool. Well, it'll be really fun to see this develop over the next couple of years, both on the data side and then the modeling side. It'll be very cool. Very nice. Stephanie, thank you once again for walking us through your very lovely article.
And thank you again for having me.
And that will do, everyone. And I hope this made your rotational astronomy day just a little bit better. And we will see you on the next one. Bye-bye.
Bye.